Okay, so if we could begin. So now we've done all the numerical derivation. Now we'll start doing numerical integration. So we will first look at the trapezoidal method, then the Simpson method, and then more advanced methods to get better approximations of the integral. So what we're looking for is methods form. So we have an integral, a definite integral from a to b, f of x dx, and then we want to find some kind of q which takes our function and also the endpoints a and b, and it should give us a reasonable answer to the integral. So before we start here, I'll give a definition of something called numerical quadrature. So def. Numerical, oops, quadrature, like so. So we will assume that we have some kind of ordered points. So these are, we start with a, it's x0, then we get x1, so these are ordered neatly, and we stop with xm, which is the endpoint b. Then the numerical quadrature, see, quad is given by, so this is our q, f, let's call them a, b here. Our f is our function, and these are the endpoints of our interval. This is going to be a sum from k0 to m, where we have some kind of weights k, which we will try to figure out, and the function evaluated at the point xk. So this will have the property that our integral from a to b, x, so x0 can be any function as long as it's decent, q of f plus some kind of error term, e of f. And then this e of f will be your error term. Yeah. So this is basically just a definition. So we will look at how to create the error as small as possible. Next, we'll see something called degree of precision, which tells us how precise the approximation is, or how high of a degree of a polynomial we can actually integrate using this method without introducing errors. Degree of, well, I guess a small p, precision. So the DOF, I'm going to call it, of Q of f, which is our approximation of the integral, is the positive integer n such that e of some kind of polynomial I is 0 for all polynomials. Basically, this means that if you have a polynomial of degree I guess I have to give some. So I has to be lower than this degree of position. Where Pi is a poly of degree I. So if we have a method of a degree of position 2, this means that we can integrate all second order polynomials without introducing any errors. If we have a degree of precision of 5, that means we can integrate all polynomials of degree 1, 2, 3, 4, and 5 without introducing errors. So this term is going to be 0. Yes. So then we'll look at the first method, the first Q, the first way of estimating this. So I will skip just a rectangular approximation, which is basically just you approximate the integral with rectangles, and I'll instead just go straight to the trapezoidal method. This? Yep. It's DOF. I guess I should have had. No, sorry, DOP, of course. Precision. What is DOF? Precision. DOP, of course. Precision, yes. It's how precise your approximation is. I mean, yeah, depending on the definition of precise, and here the definition of precise depends on the polynomials. So first, trapezoidal rule. This, I guess, is known for most of you, but it could be good with a repetition. So we'll first assume, again, that we have a interval A, B, which is divided into m subintervals. It's divided into m subintervals, like so. So we will call these subintervals xk and xk plus 1. And these subintervals, they will have a width with h, which is basically the step length, b minus a divided by m. So this will give us the distance between these 2 points. And this will give us that x of k equals a plus some kind of integer I h, where I will go from 0, 1, all the way to m. So when I here is m, xi or xm is equal to b, and if it's 0, well, then we're in the other end of our interval. So with these rules, then the trapezoidal rule is given as the trapezoidal rule is then. So sometimes it's called the trapezoidal rule, other times it's called the trapezoidal method. It's basically the same thing. So t of the function and the step length h equals h over 2 from, oops, I equals 1 to m f of k x minus I plus f of x, oh sorry, I should use I instead, like so. This then can be written, and I will try to illustrate how it looks like. So again, T rule, trapezoidal rule. You can also rewrite this sum, and you will end up with TFH equals, oops, H over 2 F of A plus F of B. So this is the endpoints, and then you have the plus all the inner points. K equals 1, 2, nope, I, m minus 1, f of x, I, like so. Well, it should be an h times this. Yes. So basically how this looks, say that we have some kind of function f we want to integrate. See, start here, like so. So this is our function of x. X like here. We will have, well, this is a start of interval a, the end b. So we will have here, and then some kind of evaluation here, which basically means we get a trapezoid going like this, and then we sum this one. We continue with the same step length. See, approximately here. Like so, I think. So you see that we are introducing some errors here, which is, let's see. Like so. So see, we are missing, in this case, we're missing a small piece here. This one we're missing a small piece here. Here we maybe have a bit too much. Here you see we have too much. Now if we're lucky, these are going to cancel each other out, but most probably they won't. But you see we are not quite there. And then you would have this h that is going to be this. You had a question?
Should be h divided by 2.
Where are we? Here?
Yep.
No. Why not? If you try to look at this sum, you will have 2 of each of them,
Yep.
except at the endpoints. Does that make sense? So yeah, then you double them and then you divide by 2. So you have 2 of them, but you divide by 2 and then you end up with 1 of them. So you see the endpoints, they are divided by 2, whereas the rest of them, since you have used both of them, then you would. Was that a good explanation? It adds up. It adds up. So you see first here you would have, let's say, x2 and 3. Next time you will have x3 and 4. Meaning that you would have 2 3s.
The first and the last one?
Yeah, they're only once. So that's why you divide by 2 here, but not over here. Yeah. I'm thinking. No. Because if it starts at 2, then you won't get this point down here. That's why it starts at 1. Because you also include this point. So you have first this and this point, and then you have this and this point. So you have this twice. So it's supposed to start at 1. So then we have the dreaded error analysis of this. So we will first look at the interval. Let's see, error. Analysis. So we'll look at the interval, or start with the interval. Start with x0, x1, which is basically the first interval. So that's this interval. And then, well, we'll try to take the integral of a Lagrangian polynomial. So integration I'm going to call it the L poly. So this is the Lagrangian polynomial P1, and it's terms yield. So before I give you the answer to what that yields, I guess maybe we should recap what a Lagrangian polynomial is. This is going to look like, have it in blue. So this P1 is f of x0, x minus xi over x0 minus xi plus f evaluated at xi, x minus x0, well, xi minus x0. That's the Lagrangian polynomial P1 here. So, x0 to xi of x dx. This is the same as x0, xi, P1, x dx plus, let's see, 0, x1, and this won't fit perfectly unless it's a polynomial of degree 1. So we'll have a rest term, which will look something like this: x0, x minus x1, f twice differentiated, and then some kind of chi here dx. This whole thing is divided by 2 factorial. So then we know that this term does not change sign. I'll just write this as well. X minus 0 minus xi. Does not change sign, yes. Does not change sign. And why? Well, we know these are ordered and they're inside the interval. So this will have the same sign. And then we assume that this is continuous. And that is a perfectly valid assumption. Most physical functions will have a continuous second derivative. This continuous, like so. This then means that we can use the mean value theorem. On this. The MVT. So, which means we will have, let's see, from x0 to x1 of x dx will be h over 2. So here I'm using this convention. So f0, this is f evaluated at the point x0. F I plus for some, so this is just a constant, it exists, we don't really know what that is, but it exists such that this relation is true. I over 2 dx. So it's just a constant again. We don't really know what it is. We don't really care. We just know that it exists. So if you change the variables, so we are going to change the variables to, let's see. So basically you're going to say that x equals 0 plus ht. So this is a perfectly valid transformation. And again, it means that dx is going to be h dt. So implicit differentiation. And what we'll get 0 x1 x dx h over 2 0 plus f, oops, fo plus this thing here, so c1. I'm going to change the 2 out of the integral. C And now we will have that this is from 0 to 1. Yes. And it will become ht. So if we look at this and I insert this x equals x0 plus ht, then we'll be left with just ht in this one. And in the next one, it will be x0 plus ht minus x0. No, x1, x0. And then we're changing the integrating variable, so h dt like so. We can then clean this up a bit. See h over 2, 0 plus 1. Then it's going to be f2 of c1. We will have an h to the power of 3 in there. Divided by 2. From 0 to 1. T squared minus t dt. And this is a definite integral we can actually solve. And we will end up with our error. Let's see. Because, let's see, minus f2 of c1 divided by 12 times h to the power of 3, like so. So I can see that this is our estimation, and this is kind of the, well, this was, and this is going to be the error term for just this first interval. Yeah. So that's only for the first interval. Next we have to sum all of them. Sure. Are any questions? No? So next. I guess we can just call them intervals. So then we will have an integral from a to b. A to b, not from x0 to x1 as we had, well, a couple of minutes ago. So we can actually divide this. See, yep. I equals 1 to m xi minus 1 to x I x dx. So what we've done here is that instead of taking the whole integral, like the whole interval at all, we're just taking a lot of small integrations. So this is equivalent, assuming that this f is a nice function, which is most probably is. Then we'll use the trapezoidal method to evaluate all of these small ones, and we will get, let's see, I equals 1 to m h over 2 f of xi minus 1 plus f of xi minus many of these error terms. H over 3, 12, sum is 1 to m f of ci 2. So that means we've summed all of these small intervals we have over here. So this is just the sum of all of these, and then plus the sum of all of these. Which leaves us with trapezoidal rule T f of h minus b minus a times h squared over 12 over the amount of subintervals I equals 1 to m f of ci 2. Yes. Then I need more space. Any questions? So we're soon there. Next, what we're going to do is just going to pick the worst CI. This is going to be some kind of number. We're just going to pick the worst because we're pessimistic when doing error analysis. So we will get at the end of x dx equals the trapezoidal of h minus, I'm gonna need more space, b minus a over 12 h squared times f to some kind of number, and then this is going to be the ET of h, which is h2. So looking back at what we did at the start of the lecture, so this is going to be our Q of f. I guess that was the notation we used. I'll do the same here. So this is our quadrature or approximation of this integral, and then we have some kind of rest term, which is of the order OH squared. So this is a pretty, well, simple approximation. We can actually do a lot better. Oop. So if you just note down this result, this is for the trapezoidal method. Next we will look at the Simpson method, or Simpsons Rule, as the book calls it. So where's the trapezoidal rule that, well, it used trapezoids. Simpsons rule is using, well, a better interpolation technique. So again, we have some kind of, let's see, maybe like this. It's your function f. And b, this Simpson method will actually sample 3 points. So if this is just one interval, it will sample the endpoints and then the midpoint. And I will then try to interpolate this into a second order polynomial, which would look something like this. And again, you see that we are introducing some error. So here we have undershot, and here we are kind of overestimating down here. Again, if we're lucky, then these might cancel out. We'll actually look later that we can actually get them to cancel out as well, looking at something called Gaussian quadrature. But that's for a later method. So we have the same starting or the same assumptions as for the trapezoidal rule, except that we'll say that, let's see, the h is going to be this instead. So whereas this is just one interval here, the h is going to be half of this. So h here is b minus a divided by 2m. Oops. Looking at the trapezoidal rule, you see that it's only just m, just one m. Simpsons rule, there's going to be 2m. We won't go into as much detail as for the trapezoidal rule, so I just summarize it. S of fh over 3 equals 1 to number of these f of x to I minus 2 minus 4 f of x to k minus 1 plus f of x to k. So again, we can rewrite this sum and end up with c is the endpoints f of a plus f of b, as with the trapezoidal rule, 2h over 3 I equals 1 minus 1 f of x to k plus 4h over 3 it's 1 m f of x to k minus 1. Let me just double check. Yes. And then you can, of course, reorganize this if you want to make it more clear. Actually, let me reorganize it. So 3 of a plus 2 equals 1 minus 1. Oops. K plus 4 I equals 1 to m f of x to I to I minus 1 plus this f of b, like so. That's, I mean, which form you prefer is preference. I like this form. And I see that I'm doing something wrong with the indices. If I've written an index k, I am actually meaning I. So apologize for this. There we have I, and I. Yes. And before doing the error analysis, I guess we can have a 15-minute break. To recap. Any questions before the break? Is this new stuff? Have you seen this before? Yes. They teach this in the math courses at NTNU at least, so should be known. We'll try to advance it after a while, but we need this background first. So yeah, small break, 15 minutes.